nothing to do with plants. These are boring numbers. This has nothing to do with plants whatsoever. But we can very clearly see that this sequence does give us phi, and we can very clearly see that phi is the answer to the optimal plant rotation. So to me, that seems like evidence of somebody saying this is a number that I'm going to have show up in multiple unrelated areas. And people will debate that until the cows come home, but that's how I see it. I think that because they are so unrelated, this is number theory, and it just somehow happens to show up in nature. And we can actually see that sort of phenomenon of having two unrelated fields show up together with another familiar constant that we know as pi. We know it as the circle constant. We're constantly taught that it's the ratio of a circle's circumference to its diameter. So this is very familiar to us. You can see that pi, if the diameter is 1, the circumference will be exactly pi. But we can actually calculate pi without using circles at all. So there is an algorithm, and you're all going to get very scared because it looks disgusting.
Like the exclamation points.
Yes. So this is the Chetnovsky algorithm. I don't understand it at all. I just put it up here because
you don't understand it yet.
So this is the most accurate calculation of pi known to man right now. It was the first algorithm to crack 1 billion digits of pi. And it's completely useless because we don't need that many digits of pi, but mathematicians get really excited about this. So it was created by a couple of brothers, the Chetnovsky brothers, and they used a supercomputer to calculate 1 billion digits of pi. And this algorithm still holds the world record for the most accurate and the fastest computing algorithm to find pi. But I'm not going to spend too much time on this because I'll get a headache. But there are other slightly less boring, but still kind of boring ways of estimating pi. If we take every odd fraction, a 1/, a 1/3, a 5th, a 7th, and so on, and we alternate subtraction, addition, we get pi over 4. Similarly, if we take every fraction and square it, we get pi squared over 6. When we add them all up, we get pi squared over 6. In both of these examples, there's not a circle in sight. So we know pi definitionally as the ratio of a circumference to the diameter. But these have nothing to do with circles. So this is sort of another example of how it can show up in unrelated field. We can even use probability, and this, I'm a math nerd. You guys might not be as excited about this as I am, but I think this is super cool. So we have a definition, we have a term called coprime, where if you take two numbers and they do not share a factor, we say they're coprime numbers. For example, 12 and 25 are coprime because they don't share any factors. 12 and 24 are not. They are cofactors because you can divide each of them by 2 or 3 or 4 or 6. So if we take the probability of two random positive integers, of them being coprime, so if we just take two random numbers, the probability that they are coprime is equal to about 60.8%. It's equal to exactly 6 over pi squared. And we don't know why this happens, but I think that's the coolest thing ever, that we can use probability, there's no circles at all, and we can find a number that we initially thought was only found in circles. So once again, this is probability versus geometry. They have nothing to do with each other whatsoever. But we can very clearly see that in this, and in this monstrosity, none of these have anything to do with circles, but they all, they all share pi. Pi is still the same in all of these different instances. So once again, I find this as evidence of an intelligent designer choosing to make this, to make this constant, to make it show up in multiple areas rather than just having, a number that happens to show up in every circle, and it also happens to show up in all of these different series because the chances of that happening are minuscule. So now I'm going to shift a little bit towards another one of my passions, which if any of you have had a conversation with me for more than 12 seconds, you know is music. And so I call this the other universal language, the first being math. So we can see similar patterns in music, especially when we're looking at the physics of it, and we're not going to get too deep into physics, so don't worry too much. But we'll just talk a little bit about how the physics of music works. So with music, what we're doing, we're combining different pitches and rhythms to make a melody, and different pitches can be physically defined as different frequencies of sound waves. So you can see by this graph that they follow an exponential curve. So rather than just going up, one whole step is equal to this many hertz, we actually we can see it on an exponential curve that as it goes up, for every octave that we go up, we double the frequency. So this can be, we can now define intervals in terms of how much the frequency goes up per interval. So we've already defined an octave as it goes up by a factor of 2. So we can figure out relative frequencies of different intervals, and I did out all the math here. So obviously, this doesn't really mean a whole lot to us, but we can see that there are a couple of numbers that sort of stand out to us. We have an octave at exactly 2.0. We have a fifth at exactly 1.5, and I'll explain sort of how these intervals work in a second. But we have this is pointing to something in music called sympathetic resonance. And sympathetic resonance is, if you've ever seen the fat lady singing and cracking the glass, if you've seen that kind of thing before, that's an example of sympathetic resonance. It's where one sound wave can cause something else to vibrate. And that's actually how you're all hearing me right now. The bones in your ears are conducting the sound waves of my voice. So it's a form of sympathetic resonance. And what we find is that there are actually certain intervals that work with sympathetic resonance better than others. So if we were talking about the intervals that sort of stand out to us, the ones that don't look like uneven types of decimals. So we have 2.0, we have 1.5, and the third as well is 1.26. So these three intervals exhibit sympathetic resonance best. So now we're going to explore that over at the piano. So if we want to get up and move to the piano, we're going to talk a little bit about something that I think is super cool called overtones. So if you guys want to gather around. So if we look at the anatomy of this piano, we have underneath the strings we have clappers, and on top of the strings we have dampers. So these stay down. The dampers stay down on the strings, and the clappers, when you hit it, come up to hit the string. So if you can all see that, this is not sympathetic resonance because I'm hitting the string to make it vibrate. But if we think about sympathetic resonance, what that would mean is that we have one sound wave causing something else to begin to vibrate. So we decided that the three intervals that work best with sympathetic resonance are the first, the third, and the fifth, which happen to be a major chord. So if the best one is the octave, which is exactly twice the frequency. So we all kind of have a concept of what an octave is. It's the same note, but just higher. So what we can actually see is that if I hold up this clapper of middle C, and I play a C up here, you can hear this string resonating with the frequency of this string, which I don't know about you guys. I think that's pretty darn cool. So we can, what I think is really interesting about this is that this isn't resonating with its own frequency. This is resonating with the frequency of this C up here. And so we can try out the other intervals, so a fifth. That's what a fifth sounds like. So if I hold down this key and I play this note, it's a little quieter, but you can still hear the G this note in this string,
Hmm.
because it's exactly
Okay.
1.5 times the frequency, and it works not as well with a third, but you can still hear it a little bit. And so if you do all of them together, you can hear the chord resonating in these strings. And so I have my piano teacher introduced me to this concept, and I've thought about it a lot because I think it's really interesting phenomenon. And so we've worked through it in a couple of different ways. So I've asked Miss Wolfskill to help me a little bit with this. One of the ways that my teacher and I use this to our advantage is if when I'm playing oboe while he's playing piano, to tune the oboe to the piano, you can lift up the pedal, or you can press the pedal to lift up all the dampers, and I play my tuning note, and if the tuning note resonates with the string that I'm trying to resonate with, then that means that I'm in tune. And if it doesn't, then I know that I need to adjust myself. So if you want to just play your tuning note, which is A, which is fine.
So you want my A or concert A?
Concert A.
Concert A. So that's going to be my E.
Mm-hmm. So if you want to come a little closer.
There it is. Okay, over there. I'm getting smooth round vibration.
Yep.
Mhm.
So you can hear it resonating in the A.
So I'm playing an E, which would be your A.
That's that sharp. That's okay, doesn't matter. So you can hear, if you want to just do it again, you can hear that she is playing in tune with the piano. Yeah. So the louder that it would resonate with this, the more in tune that she is with the piano.
So if you play your... Let's
It doesn't
have
actually
you,
matter what note it
yeah,
is, but
let's have you play... Let's have you play a C. So that should... My G should make that...
mhm. Yeah, so that's really good. She's
Oh.
very in tune. So at my senior recital, actually, I used this trick to tune myself and Jacob and Ethan all to the piano. Oh, my computer fell asleep. That's okay. So I used this trick, and it's actually it's easier and it's more accurate than just using like a handheld tuner, and it's a lot cooler too.
That's pretty cool.
So another way that I have investigated overtones is in composition. So in a piece that I wrote called Australian Rhapsody, and if you can actually help me with this as well. The piece that I wrote called Australian Rhapsody is a piano duet. So if you want to just hold down C major, don't play, just and with the beat as well, major, 7.
In both octaves.
Mhm. So what she's doing is she's holding down a chord without playing it. So the clappers are held up, but she didn't play it obviously. So you can see the clappers here or the dampers here are held up.
Your foot's still on the pedal?
Nope, my foot's
Okay.
off the pedal.
Okay.
So this creates a really interesting effect when I play it up here. And so we can hear the resonance of this down here, and it's not quite the same as just using the pedal. It's a little bit softer, a little bit more eerie. Kind of gives you the feeling of being in the clouds. And so I think that that's good. Thank you.